If there's one thing that sets SpaceX apart from every other aerospace company on Earth, it's their ability to make the impossible look inevitable. They don't just dream big, they build bigger, turning the wildest ambitions of science fiction into cold, hard metal and fire. And nowhere is this audacious blend of imagination and engineering more evident than in their crown jewel of propulsion technology, the Raptor engine. This is the story of how a startup that couldn't afford to fail built an engine that couldn't exist until it did. Picture this: 2006, a converted warehouse in El Segundo, California. SpaceX was hemorrhaging money faster than their rockets could burn fuel. 3 launches, 3 failures. Elon Musk was down to his last few million, money that would either save the company or become the world's most expensive fireworks display. They needed a rocket engine that could reach orbit without bankrupting them first. What they built was the Merlin, a no-nonsense workhorse that would become the most reliable engine in spaceflight history. The choice of RP-1 kerosene as fuel wasn't glamorous, but it was brilliant. This refined petroleum product had powered American rockets since the dawn of the space age. Dense as water, stable at room temperature, and cheap as dirt compared to exotic propellants. Paired with liquid oxygen, the same stuff that fills hospital tanks, it gave respectable performance without the handling nightmares of hypergolic fuels that could dissolve your lungs or the storage challenges of liquid hydrogen that leaked through solid metal. But the real genius was in what SpaceX didn't do. While competitors chased cutting-edge closed-cycle designs, SpaceX opted for an open-cycle gas generator. It wastes about 2% of the propellant by dumping turbopump exhaust overboard. You can see it during launch, that distinctive black exhaust streaming from the side of the rocket. Wasteful? But that simplicity meant fewer failure points, easier manufacturing, and faster development. Tom Mueller, SpaceX's founding propulsion engineer and the wizard behind Merlin, later admitted, "We could have tried to be fancy, but fancy doesn't get you to orbit when you're 3 failures from bankruptcy." The first Merlin produced 77,000 pounds of thrust, respectable but not revolutionary. By the time Merlin 1D rolled out, they'd pushed it to 190,000 pounds, while somehow making it more reliable and cheaper to build. 9 Merlins powered the Falcon 9's first stage in their distinctive Octaweb configuration. One vacuum-optimized variant pushed the upper stage. By 2020, they'd become the most flown rocket engine in human history, with over 1,000 flights under their belt. But even as Merlin engines were performing their signature party trick, propulsive landings on autonomous drone ships that made competitor CEOs spill their morning coffee, SpaceX engineers knew a hard truth lurking in the thermodynamics textbooks: Merlin would never get humanity to Mars. To understand why requires diving into the beautiful violence of rocket propulsion. At its core, a rocket engine operates on a principle so simple a child could grasp it: throw stuff out the back really fast, and Newton's third law pushes you forward. But between that simple principle and orbital velocity lies an engineering gauntlet that has humbled nations. Inside a Merlin engine, turbopumps spin at 36,000 RPM, 6 times faster than your car's redline. This mechanical monster pressurizes propellants to over 1,400 psi. A small portion of propellant diverts to a gas generator, creating hot gas to spin the turbine. After powering the pumps, this gas dumps overboard, the black smoke visible during launch. In the main combustion chamber, RP-1 and liquid oxygen meet in a carefully orchestrated spray pattern. The injector plate contains hundreds of precisely machined holes, creating fuel and oxidizer streams that collide at exact angles. Get it wrong, and combustion instabilities destroy the engine in milliseconds. Get it right, and you sustain a controlled explosion at 3,000 degrees Celsius, hot enough to vaporize steel. The combustion chamber walls contain regenerative cooling channels. Incoming RP-1 flows through these channels before burning, carrying away heat that would otherwise melt the chamber. It's thermodynamic jujitsu, using cold fuel to protect against the fire it's about to become. The bell-shaped nozzle accelerates combustion gases from subsonic to supersonic speeds. By the time exhaust exits, it's screaming at Mach 3.2. Every second, the engine throws 300 kilograms of propellant backward at 3 times the speed of sound. Newton's third law delivers 190,000 pounds of thrust pushing skyward. This design lineage traces back to Robert Goddard's experiments through the German V2 to Saturn V's mighty F1. When Elon said, "Make it simple," This is what they made, a spiritual descendant of engines that won the space race, refined with modern materials but fundamentally conservative in design. As SpaceX's ambitions grew, from reaching orbit to making life multiplanetary, simple wasn't enough anymore. Here's the dirty secret about RP-1. It's basically jet fuel with a PhD. And when you burn jet fuel at rocket temperatures, you don't just get thrust, you get soot. Mountains of carbon black soot that coats everything it touches. After each flight, Merlin engines look like they've been through a coal mine. Carbon deposits coat the injector faces, changing spray patterns. Soot clogs cooling channels, creating hot spots. SpaceX technicians spend hundreds of hours cleaning and refurbishing. For a company planning airline-like flight frequency, this was like building a 747 that needed complete engine overhaul after every flight. But the real limitation was more fundamental, the iron laws of chemistry. RP-1 engines max out at around 311 seconds of specific impulse at sea level, maybe 348 seconds in vacuum. Specific impulse, measured in seconds, is the rocket scientist's miles per gallon. And 348 seconds, while respectable, isn't enough for Mars. The tyranny of the rocket equation is brutal. Every pound of cargo requires multiple pounds of fuel. Every pound of fuel requires more fuel to lift that fuel. It's an exponential curve that makes long-distance space travel monumentally difficult. Improving specific impulse by even 10% can mean the difference between a one-way suicide mission and sustainable transportation. SpaceX ran the numbers, and the numbers were merciless. With RP-1 engines, a Mars mission would require 6 or 7 refueling launches just to get one ship on its way. The engines would be scrap after one use. The carbon buildup would make rapid reusability impossible. The business case collapsed. The dream of making humanity multiplanetary would remain just that, a dream deferred by chemistry. They faced a crossroads. Keep optimizing an inherently limited technology, or start fresh with something revolutionary. They chose revolution. They chose methane. And in doing so, they chose to tackle one of the most difficult engineering challenges in rocket propulsion, the full-flow staged combustion cycle. Methane, CH4, 1 carbon, 4 hydrogen, the simplest hydrocarbon, the stuff that heats your home, and possibly the key to making humanity a spacefaring civilization. The advantages read like a wish list. Methane burns clean, no soot, no carbon buildup, no extensive refurbishment. It's 6 times denser than hydrogen, meaning smaller tanks, lighter structures. It can be chilled to similar temperatures as liquid oxygen, simplifying the plumbing. No more separate insulation systems, no more complex helium purges. But here's the real magic. You can make it on Mars. The Sabatier reaction combines Martian CO2 with hydrogen from water ice. Add catalyst and heat. Out comes methane and water. Your rocket fuel depot isn't in Florida. It's waiting at your destination. Robert Zubrin proposed this in the 1990s, but it remained theoretical. SpaceX decided to build the engine that would make it real. Yet, switching fuels was just the appetizer. The main course was the engine cycle, full-flow, staged combustion. While Merlin's gas generator throws away 2% of propellant running the pumps, Raptor sends everything, every molecule, through the main chamber. Nothing wasted. Everything contributes to thrust. Raptor uses 2 preburners, miniature rocket engines in their own right. One runs oxygen-rich, creating hot gas to drive the oxygen turbopump. The other runs fuel-rich, powering the fuel pump. Then both streams merge in the main combustion chamber, burning completely and efficiently. The engineering challenge defies description. The oxygen-rich pre-burner operates at 700 degrees Celsius with gas that desperately wants to turn any metal into rust. This is fire that burns metal. The Russians tried this with the RD-270 in the 1960s. After spectacular failures, including one explosion that left a crater where the test stand used to be, they declared it impossible. SpaceX made it work through exotic metallurgy, precise manufacturing tolerances measured in microns, and bloody-minded determination. Special nickel-based superalloys resist oxygen attack. 3D-printed cooling channels maintain precise temperatures. Computational fluid dynamics modeled combustion down to the molecular level. The result? Chamber pressure of 300 bars, 4,350 psi. like containing the pressure at the bottom of the ocean inside a bell-shaped furnace. SpaceX built an engine operating at conditions more extreme than the deepest ocean, hotter than lava, with chemicals that want to burn through any containment. Starting a Raptor is like conducting a symphony where every instrument is a bomb. The sequence begins with careful propellant conditioning. Liquid methane at minus 161 degrees Celsius. Liquid oxygen at minus 183 degrees Celsius. Both must flow at precisely controlled rates. First come torch igniters, pilot flames to trigger the main event. At T-minus 1.2 seconds, the oxygen pre-burner lights, creating 700-degree gas spinning the oxygen turbopump. The fuel pre-burner follows. Then main propellant valves open. Methane and oxygen spray through hundreds of injectors into the main chamber. The torch igniters trigger ignition. Suddenly, 3 linked combustion zones work in perfect harmony. When it works, it's beautiful. A pillar of blue-white flame so bright it hurts to look at. A Raptor at full throttle consumes 650 kilograms of propellant per second. Exhaust velocity exceeds 3,600 meters per second, 40% faster than a rifle bullet. The thrust could lift 230 tons straight up. Early Starship tests were spectacular failures. SN-8's flight ended when Raptors failed during the landing flip. SN-9 suffered startup failures. Each failure taught SpaceX something new. By 2023, they could reliably light 33 Raptors simultaneously, a choreography that would have been fantasy a decade earlier. The numbers make aerospace engineers giddy. Raptor 2 weighs 1,600 kilograms, yet produces 230 tons of thrust. That's a thrust-to-weight ratio of 143, 1, embarrassing the Space Shuttle's RS-25 and Saturn V's F-1 at 94. When 33 fire together on Super Heavy, they generate 7,590 tons of thrust, twice the Saturn V, from a vehicle designed to land and fly again. The acoustic energy could level buildings. The water deluge system flows 100,000 gallons per minute just to protect the pad. The best part is no part. The best process is no process. This Musk mantra drove Raptor's evolution from complex prototype to mass production marvel. Raptor 1 was a masterpiece of complexity. Hundreds of sensors, redundant systems. Musk took one look and started deleting. The transformation was brutal, but effective. Raptor 2 has 30% fewer parts while producing 20% more thrust. The combustion chamber emerges from a 3D printer with cooling channels following mathematically optimal paths, impossible through traditional machining. What once required hundreds of welds now emerges in days. SpaceX builds Raptors in under a week for less than $1 million. When your Mars rocket needs 39 engines and you're planning hundreds of flights, manufacturing efficiency becomes destiny. The production line resembles a car factory more than aerospace. Standardized workstations, common tools, statistical process control. This isn't just about engines. It's about enabling a future that transforms humanity from a single planet species to something more. With launch costs below $10 per kilogram, space doesn't just open, it explodes outward. Solar satellites become cheaper than coal. Asteroid mining transitions from fantasy to quarterly earnings. The moon becomes a gas station to everywhere else. A single Starship delivers 150 tons to Mars, an entire base in one landing. Life support, power systems, construction equipment, fuel production machinery. The same vehicle launches from Earth, lands on Mars, refuels using local resources, and returns. Not a mission, a transportation system. Not flags and footprints, the beginning of interplanetary civilization. In a Hawthorne warehouse, production workers assemble machines embodying humanity's highest aspirations. Each Raptor rolling off the line is a statement. The future doesn't wait for permission. They didn't just build a rocket engine, they redefined what's possible. The revolution happens quietly. While committees debate, SpaceX builds. While competitors dismiss, they iterate. With methane, metal, and stubborn refusal to accept limits, they may have changed the future of life itself. Watch those 33 points of light beneath Super Heavy. Each burns with the intensity of human ambition. Each promises, we're just getting started. Raptor's greatest achievement isn't thrust or efficiency. It's proof that dedicated engineers can still change which worlds we can reach. They didn't just build a rocket engine, They redefined what's possible. And in doing so, they may have changed the future of life itself.